There we go. All right, good morning. Welcome to Office Hours Week 4 edition. As always, I will be giving priority to humans who are here and live with questions. But in the absence of any, I'm going to be checking my email. And I know I got a couple in yesterday. And so anyways, if you're here, show up, ask a question, I will answer it. If not, I will look to the email. Good morning. All right. All right, hang on. Oh, two different emails. All right. Okay. So oh. So I only have one in my inbox. I only have one in my inbox, and I'm looking. Okay. So I see yesterday and Sunday. Here, let me. No, I just have one from yesterday. Maybe you could try sending Sunday's email again, because I didn't. There's just there isn't one in my inbox, so it must not have sent or didn't go through. Totally. But I can get cracking on this deal. Okay, so all right. So here's first example. There we go. Determine the total number of lone pairs in the Lewis structure of NiH2. All right. And there's a couple more that come after this. Okay, so first we have to draw the Lewis structure, which means that we have to calculate our total number of electrons. We're going to do that using our periodic table, not obscured by text, of course. So when you're determining the number of valence electrons, what you want to do is look at, again, we're looking at the main group. So just our main group elements. Because again, we're not doing Lewis theory for transition metals. Kate, good morning. Good to see you. So again, what you do is you identify the column of the main group, and actually, for this method, I should point out that helium belongs in that second column. So this is the 8th column. All right, so we're going to identify where nitrogen is. Nitrogen being in the 5th column has 5 valence electrons. Hydrogen, because it is in the 1st column, has 1 valence electron. But because we have 2 of them in this molecule, we got to multiply that by 2. And then iodine iodine is in the 7th column, so it is bringing 7 valence electrons. And we have to add all of these up to get our total electron count. So we're going to have 9, 14 electrons. All right, so we have a budget of 14 electrons to spend. Now we need to select our central atom and attach everything else to it. All right, now to make a bond costs 2 electrons. So 2, 4, 6, right? We're making 3 bonds. We subtract that from our budget, leaving us with 8 electrons. All right. Next, we need to complete our octets. Hydrogen is satisfied, right? Because it has 2 electrons each, and that's all hydrogen wants. Nitrogen needs 8 electrons, so we will give it 1 lone pair. Subtract 2 from our budget, leaving us with 6. Iodine right now has access to 2 electrons. It wants 8 like nitrogen, so we need to give it 6 more electrons. We have 6 in the budget, so we give it 3 lone pairs. So now we've spent all of our electrons. This is our Lewis structure for the molecule. Now, if you look at this molecule, we've been asked to determine the number of lone pairs here, all right? The number of lone pairs. Nitrogen has 1 lone pair. Iodine has 1, 2, 3. So we have a total of 4 lone pairs in this molecule. Does that make sense? The next question is actually. Oh wait, no, it's totally different question. So it's related, but not exactly the same. So if we look, so the next example is determine the molecular geometry of, give myself a little more room to work with, NiBr2. All right, and this has to begin the same way the last problem did. So if we're going to determine the molecular geometry, we need the Lewis structure of this molecule. So again, looking at the columns of the periodic table, we've got nitrogen, bromine, and iodine. All right, so we have nitrogen, which has 5 valence electrons. iodine, which has 7, and we have 2 bromines, which have 7 each, so together they bring 14, which gives us 26 electrons to start with. Alrighty, so we're going to start by throwing our central atom in the mix and attaching our 3 others. This is going to take 2, 4, 6. Leaving us with 20. Now, when you look at bromine, bromine has access to 2 electrons. It needs 6 more. We have 6 in the budget. Leaving us with 14. So we can give bromine a full octet. This bromine also needs 6, and we have 6 in the budget. So that'll leave us with 8 electrons. Iodine needs another 6, and we have 6 in the budget. So we give iodine 6 electrons, leaving us with 2. And now nitrogen needs 2, and we have our last 2 electrons in the budget. So that works out. So here's our Lewis structure. We weren't asked to draw the Lewis structure, but we needed to, en route to determine the answer, we need to find the molecular geometry. Now, to do that, we have to look at our central atom. So nitrogen is our central atom, and around our central atom we have 3 atoms and 1 lone pair. So that's 4 electron groups, right? 4 electron groups, or electron clouds, which means that the electronic geometry is tetrahedral. But when you have a tetrahedral electronic geometry with 1 lone pair, that means that your molecular geometry is trigonal pyramidal. All right. Awesome. Okay, hitting up this last, the last question in this email. These are all on kind of a theme. This is another, what are the, determine the number of lone pairs in, now your question said NH4, but I think it's missing a piece of information. I think it has to have a charge of +1. Um, so if you were trying to determine the number of lone pairs in NH4, you wouldn't be able to draw the Lewis structure. It is NH4 plus. So if your source material was missing that positive charge, then there's an error in it. All right. So again, this starts the same way it all starts. We have to total our valence electrons. Nitrogen has 5. Hydrogen has 1, but we have 4 of them. All right. But then we have to deal with this positive charge. If you have a charge of positive 1, that means you have 1 fewer electrons than you should have. So you actually have to subtract 1 electron when calculating your budget. So we will have a total of 8 electrons. Placing our central atom, nitrogen. We need to attach all our hydrogens to our central atom. This is 2, 4, 6, 8. You'll notice that it takes our entire budget to attach our hydrogens to our central atom. Adding my positive charge to the outside. Everything, the offset rule is satisfied, so there's no further work, and you'll notice this structure has 0 lone pairs. So that is, that's that. Alrighty, so Will, let's hit up Will's question, which is how do you determine the electronic geometry? And what I'm going to do is kind of do a quick review of electronic and molecular geometry. So when you're trying to assess, when you're analyzing what shape is a molecule going to have around the central atom, you know, what geometry is it going to have? You need to determine the number of electron groups, and so this is kind of where things start. Electron groups often get abbreviated as EG. All right, so electron groups are, there are 2 things count as a group of electrons around your central atom. All right, and they are one atom is 1 electron group, and 1 lone pair equals 1 electron group. All right, so so with this in mind, if I gave you some molecules and asked you, okay, how many electron groups are around the central atom? Let's do it for these molecules. And I guess I should state this explicitly. These are, when you're counting the number of atoms and number of lone pairs, something that you should keep in mind. We are only concerned about the atoms and lone pairs attached, or I should say, on the central atom. On the central atom only. All right, so if we look at the examples that I've drawn out here, there we go. So if you look at the number of atoms on H2O, we have two atoms, and we have two lone pairs, so that means we have 4 electron groups. All right, when we look at the next example, carbon dioxide, we have 2 atoms on the central atom. And you'll notice that we have 0 lone pairs. Because we're not looking at lone pairs on the whole molecule, we are just looking at lone pairs on the central atom. So we have 2 electron groups. When we look at our next example, nitrite, nitrite has 2 atoms. And 1 lone pair. There's 3 electron groups around nitrate. All right, so that's how you identify the number of electron groups around your central atom. You look at lone pairs on the central atom. You look at atoms on the central atom. And the number of electron groups around your central atom, these determine your electronic geometry. All right, those determine your electronic geometry, and here's how. For Chem 305, there are only 3 electronic geometries you need to know. All right, there is linear, over here. Sorry, these are electronic geometries. All right, there are 3 electronic geometries. There are linear, trigonal planar, and tetrahedral. All right. I'm just going to restructure this. There we go. And what determines the electronic geometry is the number of electron groups around your central atom. So to determine your electronic geometry, you have to identify your electron groups. If you have 2 electron groups, you're going to be, linear. If you have 3 electron groups, you're going to be trigonal planar. And if you have 4 electron groups, you're going to be tetrahedral. It's that straightforward. Now, electronic geometry looks at all of the electron groups. The molecular geometry is slightly different, all right? There are 6 molecular geometries you need to know. And your molecular geometry is determined by your electronic geometry together with the number of lone pairs in your molecule, all right? So I'm just going to touch on that just to be thorough, just because you might look at the electronic geometry and go, okay, no, but then how do I do the next step? Because you'll be definitely asked for molecular geometry on the exam. So what determines your molecular geometry is your electronic geometry and your number of lone pairs. All right, so let's line this up. All right. So electronic geometry. Lone pairs plus lone pairs on your central atom, again, determine your molecular geometry. All right, so we've got your electronic geometry plus your number of lone pairs determines your molecular geometry. All right, so if your electronic geometry is linear, the cool thing is, if your electronic geometry is linear, we can skip the lone pairs part and go straight to the molecular geometry. It will always be linear. That is a 1-to-1 ratio. All right, that will always be the case. Now, if you have a trigonal planar, paired together with 0 lone pairs, all right, if you've got no lone pairs, then your molecular geometry is going to be trigonal planar. Anytime you have no lone pairs on your central atom, the molecular geometry and electronic geometry will be the same. It's when you change it, when you actually add lone pairs to the mix. So if you're trigonal planar, and you have 1 lone pair on your central atom, this is where things change. Your molecular geometry ends up bent. It's called bent. So these are the first 3. Let's look at the last 3. So let's say your tetrahedral, whoops. Tetrahedral together with 0 lone pairs. Anytime you have 0 lone pairs, your electronic and molecular geometries are the same. If you have 1 lone pair, your molecular geometry changes to trigonal pyramidal. And if you have 2 lone pairs, your tetrahedral geometry becomes bent. And all that's in the lecture. This is kind of the quick kind of review. Will, I know you're not here with us now, but you're going to go back and watch later. If you want an more in-depth deep dive into molecular geometry, which I know is not what you asked about, I just wanted to cover it to be thorough, then you can hit me up in office hours, send me an email, and I can really dig into what these shapes look like and all that stuff. Again, I drew them out in lecture, but if it's still unclear, I can totally go through it in greater detail. All right, there were a couple other emails that I want to get to before. Okay. Okay, so there's an email request about stoichiometry. So let's do a stoichiometry example. Oops. Write a balanced chemical equation for the reaction between silver 1 nitrate and magnesium chloride. That forms silver 1 chloride and magnesium nitrate. All right, so here we have a reaction between silver nitrate and magnesium chloride, forming silver chloride and magnesium nitrate. We need to balance this chemical equation. So first off, Let's look at our reactants. All right, silver, we've actually been told silver has a charge of +1. Nitrate is a polyatomic ion, one of the ones you just got to know. It's NO3 with a -1 charge. So these combine in a 1-to-1 ratio, AgNO3. Now, magnesium and chloride, we have to look at the periodic table. When you do, you'll see that magnesium has a charge of +2. Chloride has a charge of -1. So these combine in a 1-to-2 ratio. For every 1 magnesium, we need 2 chlorides to balance. All right, those are our reactants. Our products are silver chloride and magnesium nitrate. One of the cool things for this particular reaction, it doesn't always work out this way, but we've already figured out what our ions, what our charges are. So we have magnesium nitrate, magnesium paired with nitrate, and silver paired with chloride. So silver chloride is going to be a 1-to-1 ratio because it's a -1 and a +1. Magnesium chloride is going to be a 1-to-2 ratio because we need 2 nitrates to balance our magnesium. Now, whenever you have more than 1 polyatomic ion, you have to show that by placing it in a parentheses and putting that subscript on the outside of the parentheses. All right, so now we need to balance this chemical equation. I'm going to actually blank this out, move this up to give us more room to work. All right, now when we're balancing a chemical equation, you can't alter any of the subscripts because that fundamentally changes the compounds present in the reaction. That makes it a different chemical equation. So you can't ever change your subscripts. You can change the stoichiometric coefficients. You can multiply the entire molecule by a number. All right, now at the beginning of any balancing problem, I always write a inventory of the atoms on both sides of the reaction. Some people are really good at this. They can do it in their heads. I'm not. I've never been one of those people. So I always write out every element. And then I compare. I take an inventory, I compare. We have on our reactants side, 1 silver, 1 nitrogen, 3 oxygen, 1 magnesium, 2 chlorine. On the product side, we have 1 silver. Let's see, we have 1 times 2, so 2 nitrogen, 3 times 2, or 6 oxygen, 1 magnesium, and 1 chloride. Now, when you're balancing chemical equations, this is one of the rare times in life where taking the path of least resistance is the best way to go. Always go for the easy stuff first. For example, I notice that I have 2 chlorines on the reactant side and only 1 on the product side. I need to have 2 for this thing to be balanced. So I am going to multiply silver chloride by 2. This will balance my chlorine count, but it throws my silver count out of balance. I'm not worried though, because I know how to solve that problem. I just need to multiply the molecule that has silver in it on the reactant side by 2 as well. So this will change my silver count, but it also changes nitrogen and oxygen. But check this out. Now I have 2 silver, 2 nitrogen, 6 oxygen. that act of balancing silver has actually balanced both my nitrogen and oxygen in one fell swoop. So this is the balanced chemical equation. Basically, how you decide what needs to go where is you look at all the elements on both sides and then just figure out a way to get the same number of elements on both sides. Just like I did, I saw that I had 2 chlorine on the reactants, 1 on the products. So I multiplied that molecule by the number that balanced it. It created other quote-unquote problems, but then you just go and iron out those problems as you go. All right. Let's see, I've got a couple more questions in my email that I want to get to about homework 3. Let me pull that up. All right, let's see. All right, problem 7, 7, 9, and hang on, 7, 9, and 14. Okay. There we go. All right, let's look at, okay, so here is, this is going to be a lightning round. All right. So starting with number 7. All right, so number 7 is name this compound. All right, and I am going to consult our trusty periodic table on this one. So aluminum, you'll notice, is a main group ion. Selenium is a main group non-metal. Sorry, aluminum is main group metal, non-metal. So the way you name ionic compounds are name of the cation, name of the anion. Because aluminum's main group, we don't need to worry about the charge. So this is going to be aluminum. Now Se, which is selenium, we know when we're naming ionic compounds, you chop off the end and add "ide." So this is going to be aluminum selenide. All right, and that is homework problem number 7. Let's take a look at number 9. Let's see, number 9. Which one of the following compounds has a formula that contains parentheses? Okay, interesting. Interesting question. Here we can zero out our periodic table. Or maybe we'll need to bring it back. Let's see. So which compound has a formula all right. So here's a good question to ask. What kind of formula has a parentheses? And there's only one type of chemical formula that will contain a parentheses, and that is a compound with multiple polyatomic ions. All right, a compound with multiple polyatomic ions will is the only type of formula that has a parentheses. So that's what we need to keep in mind. That's what we're on the hunt for as we look at these following options. So we have strontium hydroxide, ammonium hydroxide, lithium hydroxide, and barium carbonate. All right, so what you have to do is basically you have to write out each chemical formula, identify the one that has more than one polyatomic ion in it. For barium carbonate, barium, if you look at the periodic table, takes a charge of +2. Carbonate is -2, so this is 1-to-1. That's just going to be the two smashed together. If you look at lithium hydroxide, lithium is +1. Hydroxide has a charge of -1, so again, that's a 1-to-1 ratio. Ammonium hydroxide, let's take a look. Ammonium's a polyatomic ion whose charge is +1. Hydroxide is -1, so that can't be it. Strontium hydroxide. Strontium has a charge of +2. Hydroxide has a charge of -1, so check this out. We need to include 2 hydroxides in this molecule. The only way to do that is with a parentheses. So the correct answer to number 9 is strontium hydroxide. All right, let's take a look at homework problem number 14. This will close out office hours for the day. let's see. Which of the following ionic compounds would have a name that contains the Roman numeral 3? Okay. All right. Again, we're going to do a similar analysis to what we did last time. What type of compound has a Roman numeral 3 in its name? And the answer is a transition metal. Has to have a transition metal. With a charge of +3. All right. So let's go ahead and look at the options that were given. There we go. So our possible answers are FeBr3, AlCl3, Cu3n, MoSO4, 3. Then we have two more options. More than one, or I should say, be a little more concise for us, multiple correct. Oops. Multiple correct. None correct. All right. So first off, we've been asked to identify a compound that has a transition metal with a charge of +3. So the first thing we want to do is we're just looking for items to eliminate. And the first one that jumps out at me is, you'll notice, so let's find these candidates, all right? Iron is a transition metal, so that's a possibility. Aluminum is not a transition metal, so it will not have a Roman numeral 3 in its name. Let's see, copper is a transition metal. Molybdenum is a transition metal. So we know aluminum's not a candidate, but iron, copper, and molybdenum are all possibilities. So the next step, the first, because remember, it's anytime you're doing multiple choice, you're running through process of elimination. The next step is we need to see, do any of these, or possibly multiple of these, have a charge of +3? All right. So let's blank out our periodic table. And let's take these one at a time. So taking a look at iron, the first thing we're going to do is we're going to look at, well, we need to find the charge of iron. This is paired with bromine as an ion. Bromide, if you look at the periodic table, determine its charge. It has a charge of -1. And we have 3 of them in this molecule. That means that iron will take a charge of +3. So one thing we know right off the bat is this is a correct answer. We can't stop the problem because we have to figure out, are there multiple correct? But we know at least we have one right answer. Now let's look at copper nitride. So we have 3 coppers, and we have 1 nitrogen as an ion. Nitrogen is nitride, and it has a charge of -3. Because we have 3 coppers, that tells us that copper has a charge of +1. If we've got 3 of them to balance against a -3, each one must be a +1. So that will not have a Roman numeral 3 in its answer. For our final candidate to analyze, let's look at molybdenum sulfate, or that's not its name, but the one with molybdenum and sulfate. So sulfate has a charge of -2, and we have 3 of them. Here, leave myself enough space. All right. So if we have 3 sulfates, each one is -2, that means molybdenum has a charge of +6. So of our 3 transition metals, iron's the only one with a charge of +3, which means that we can cross out multiple correct and none are correct because we have 1 right answer and only 1 right answer. So FeBr3 is our only compound with a Roman numeral 3 in the name. Alrighty, so real quick before we go, there's a couple questions in the chat. First is, can we have more office hours? And I'd say right now, at this moment in time, our 1 office hour a week has been enough to like meet the needs of the class, the questions that are coming in. So as of right now, it's meeting our needs, so I don't see the need to expand it. If you feel the need to have more one-on-one time, totally hit up the Folsom Lake College Tutoring Center. They offer free tutoring, electronic tutoring. You can get one-on-one sessions with students who have passed this class that you're taking with a high grade. So if you're feeling the need for more one-on-one tutoring, I would totally hit that up. I know you, Sourdeep, you've been the main person to be here live. So far up to this point in the summer session, it's kind of felt like a one-on-one tutoring session, which is awesome. But this is not, office hours is not to provide one-on-one tutoring directly from me to every student in the class. There's not enough time for that. So at this moment in time, it's meeting the needs of the whole class. If you need more personal attention though, hit up FLC Tutors. They're awesome and they're free. So it's the best price point, and really good help. Yeah, you totally can. You can totally see what you got wrong on exam 1. I believe I opened it up. I'll double check in Canvas, but I believe it's open. You can review it. It doesn't give you the explicit answer, but it will show you which ones you got wrong, and then you can work those problems and solve them. And then the question, do we have extra credit work on Canvas? No extra credit has been assigned at this point. Alrighty, and that draws us to an end of our office hours. We went a little bit over today, but that's cool. This is the first one where it was like questions all the way through, which is awesome. I'll catch you guys next week. Take it easy.